All right, it looks a lot more normal now. Is everyone able to hear and see?
Yeah, we can see it says Zoom, right?
Yeah. Okay, but you should be able to see my desktop though. I mean, it says Zoom. Yes, it does. I'll tell you, I'm going to turn on Moodle and let's make sure you can see what I'm doing there. Now I don't trust it. I'm not confident that it's showing you what it's supposed to do. Anyway, so the links are in Moodle. There's two very interesting videos that I think we could use some videos after all that homework. And it's exciting, it's interesting, it's fun. It makes you look at math in a different way, especially the concept of infinity, which is a very mysterious concept. It's very difficult to visualize. In fact, it wasn't thought of for quite a few centuries after the numbers that we use were invented. It was something that came afterwards. But anyway, the interesting part about all this is that there's different kinds of infinities. That's the scary part. It's not just a single concept. There can be many different kinds of infinities. So what I'm going to do as usual is I will put the link in the chat box. Okay. And then you can watch it on your own computer. This is called the Infinite Hotel Paradox, and I think you'll have a lot of fun with it. So, all right, let's check it out.
of the next prime, 5. The following bus, powers of 7. Each bus follows powers of 11, powers of 13, powers.
Okay, are we done? Very good. So was that pretty thought-provoking? Yes. Like you said, that whole strategy was based on the idea that we're only looking at the so-called lowest level of infinity, meaning the natural numbers, which we'd studied, are infinite, and yet so are all the real numbers. But the real numbers have more numbers than the natural numbers. So how can they both be infinite? See, that's the strange part. It means that the real numbers are at a higher level of infinity than the natural numbers. And so it leads to a lot of very bizarre ideas. So anyway, now the next one is more about real world strange things that you'll discover about numbers and prime numbers. Okay. I should remember last time we watched this, there's some interesting things in here and there's stuff in here that's just kind of silly, but it's still worth checking it out. So let's look at this. Let me get you the link. And we'll see what this is all about. All right, here we go in the chat room. And let's check this out.
Don't forget to like and subscribe.
Okay, I guess we're done. So yeah, I mean that had some interesting things and some things that were kind of a little ridiculous, but it was kind of fun. So anyway, now if you remember, we're still sort of in the middle of our discussion about sequences. And so we started to talk about arithmetic sequences, and we saw how to figure out which term is or identify a specific term in an arithmetic sequence. Now, where we left off is sums of terms. Okay, so first let me save this real fast. And then we'll carry on from there and we'll revisit our discussion about sequences. Okay, so let me just quickly. Okay. Let's save that. All right, so let's scroll down to where we left off. So remember when we introduced sequences, there are two basic types, arithmetic and geometric. And so the arithmetic ones we've been looking at for a while now, and an arithmetic sequence is a sequence where each term has a common difference. Okay, so these are some examples that we looked at. 1, 2, 3, 4, obviously, because there's a common difference of 1. 2, 5, 8, 11, 14 is an arithmetic sequence because they have a common difference of 3. 10, 9, 8, 7, 6 is an arithmetic sequence because the common difference is -1. Okay, so the pattern never changes. The 3 dots indicate that these go up to positive infinity in the first 2 cases and down to negative infinity in the last case. So there's an infinite number of terms in these sequences. The important detail is the pattern, all right? So the pattern is what we're trying to identify. Now, once we know the pattern, we can easily figure out the identity of a given term. Like for example, with this 1, 2, 3, 4, it's pretty clear that the 10th term is just 10. But for most sequences, it's not so obvious. So we need a formula that helps us do this in order to avoid having to write them all out. So we've introduced this formula. And so AN means the nth term, which is what we're looking for. The first term is A1. N again is the number of the term that we're looking for. And then finally, D is the common difference between the terms. So here, for example, we took the sequence 10, 9, 8, 7, 6, etc. And we use that information to find the 10th term, A10 that is. So based on this formula, we needed to know A1, which is 10, the first term, the number of terms we're looking for, which is 10, and finally D, the common difference is -1. And so when we plugged in those numbers, we found that in this case, the 10th term would have been 1. And if you're not sure, if you're not convinced, you can write out all the terms and find the one you're looking for, and you'll see that it is in fact a 1. But that's going to take a while. So, after a while, eventually your best bet is to use the formulas. But yes, you always have the option of confirming these by writing them all out. Now, by the way, if you run into a case where you really want to see all the terms, if you have a copy of Excel, which I strongly recommend everybody learn at some point, Excel has the ability to do this for you. So let's say, for example, I type in the numbers 10, 9, 8, 7, 6. And let's see. So in other words, suppose we're not sure if the 10th term is 1. Excel can recognize the pattern that it created here. And what I can do is simply grab these numbers and drag them down until I get down to term number 10. And so sure enough, this row represents the 10th term, and it is in fact 1, just as we predicted. And this will go on forever. I mean, you can do this as long as you want. I mean, I can drag this down to term 100 if I want to. Not a problem. Look, it just takes a minute. And it's recalculating and saying, well, all right, so term 100 is -89. And so we could have done that with our formula. But if you have access to Excel, you can also use its built-in capabilities to come up with the correct term in a given sequence. Okay. So if you're using Excel already, you might want to lean on this thing and get some good use out of it. All right. Now, we did several examples here, but we also sometimes want to know the sum of the first n terms. And so rather than having to do it ourselves, there's a formula that will do this for us. So what's different here is that SN stands for not the nth term, but the sum of the first n terms. Now, these terms you hear, none of these are new. N is the term you're looking for. A1 is the first term. This is the nth term. And of course, here's 2. So let's just say, for example, our arithmetic sequence is actually, I'm going to copy this onto the next page. There we go. 1, 3, 5, 7, 9, 11, et cetera, et cetera. And you can see this is definitely an arithmetic sequence because there's a common difference of 2. Here's A1. Suppose I wanted to know the sum of the first 5 terms. That means that n is 5. And therefore, I also need, in this case, to know the value of A5. Now, if you notice, I don't need, for the formula, the intermediate values. I just need the first and the last. Now, clearly, if you look at these carefully, you can see that this just adds up to 25. Well, why don't I use this new formula up here? So S5 will give me 5 times 1 plus 9, all divided by 2, equals 5 times 10 over 2, 25. So now, of course, there's only 5 terms. And you might want to double check this, but the formula will be quicker. If there's more terms, let's say there's 20 terms, you probably don't want to add them up yourself. It's probably better to use this formula. Now, in Excel, we can do the same thing. In fact, let's go back to our friend Excel. Now, here I don't have to take this any further. I can already see, let me just hide these for a second. These are terms 1, 2, 3, 4, 5, 6. I only need the sum of the first 5. So what I would do in Excel is type equals sum, and I'll select the ones I'm interested in. And look how easy this is. It's 25, no problem. So there you can double check it, but for the tests, you're expected to be able to demonstrate that you know how to use this formula, but you can feel free to double check your results in Excel if you choose to do so. But I want to see that you can use the formula. And this will work for any arithmetic sequence. You can see this is the final result. So let's grab this formula. Now I'm going to challenge you to find out the sum of the first 6 terms. Okay, you can add them up if you want to, but I'd like you to use the formula. Now, by the way, what if it doesn't show the first 6 terms? You might have to fill in the ones that are missing. But if they're already there, you can just use this formula, which is kind of nice. All right, I'll give you a couple of minutes. So what you should probably do first is identify these variables. This is A1, this is A6. Now, if you want to simplify, you can turn this into 3 times 26, and you end up with 78. Now, if you want to double check this on your calculator, you can certainly feel free to do so. Or guess what else you can do? Let's come over here and look at Excel. And we're adding up the first 6. So I'll put equals sum. And 78. Yes, it is in fact 78. So this is not difficult. The only thing is, like I said, if the sequence only shows the first few terms, let's say that you were not shown A6, it only stopped at A5, you can easily determine what A6 is by noticing what is the common difference. Okay, so it's not always the case that you'll be shown all of the terms, but as long as you can see the pattern, you should have no trouble figuring out what's missing, and then you can use the formula. All right, so that's pretty much our discussion about arithmetic sequences. So now we're going to take at least a peek at geometric sequences. Oh, by the way, so because we're not completely done here, remember the chapter 5 problem set number 3, we're going to save it for next Thursday. All right, we're not quite done, so we'll save it for next Thursday because there's a lot of questions about this stuff in the 3rd problem set. Okay, so you have a week to do that one. In the meantime, we'll just finish this chapter and then we'll start 6, which is more, it's basically an extension of this chapter. A lot of topics that we didn't get to here, we'll see in chapter 6. All right, so what is it that makes a sequence geometric? Well, instead of a common difference, we have what's called a common ratio. Okay, so let me show you what that means with a couple of examples. All right, so now if you look at this first one, you can see there's no common difference. The difference between these two terms is 1 and then 2 and then 4. This is clearly not arithmetic, but if you notice, to go from one term to the next, I've multiplied the previous term by 2. And so we say that the common ratio is 2. In other words, what I'm doing is doubling each number as I go along. So 2 is 2 times 1, 4 is 2 times 2, 8 is 2 times 4, et cetera, et cetera. Here we say the common ratio is 2. Therefore, this is a geometric sequence. Now for this next one, the common ratio is 3. So to go from 2 to 6, I multiplied by 3. Then to go from 6 to 18, again, I multiplied by 3, et cetera, et cetera. In other words, I'm tripling each term as I go along. And once again, that means this is a geometric sequence. And finally, in this last case, you can see now you're getting the point. The common ratio is 5. I'm quintupling every term as I go along. Now, because these have a different pattern than the arithmetic sequences, it stands to reason that the formulas will also be different. The formula for finding a specific term and the formula for finding the sum of terms will have to be different. And they are. They may appear to be a little scarier when you first see them, but they're really not. What's changing now is that I need exponents. All right. So let me just quickly show you the first one. How do you find a specific term in a geometric sequence? For this one, all we really need is the starting value and the ratio. And of course, is the number of terms that we're looking for. And so this is our new formula. This now tells me how to find term an in a geometric sequence. And you notice, like I said, there's a ratio and there's an exponent. So you can tell this one apart from the arithmetic case because that one had a D in it. This one has an R. All right, so let's look at an example. And by the way, you can do this in Excel too. It has that capability. Let's look at this one. Is this a geometric sequence? Yes. How do you know? Because as I move through the terms, each time I'm doubling. Now, it should be pretty, now this is A1, by the way. This is A2, A3, A4, A5. You should be able to figure out the 7th term without this formula. A6 would clearly be 32, and A7 would clearly be 64, but let's use the formula. And you'll see it's really not that difficult. So we already know the answer, but let's check it out with our formula. As long as we have it, we might as well put it to good use. All right, here we go. So all we need to know is the fact that we're looking for the 7th term, n is 7. The common ratio in these terms is 2, and A1 is 1. It started at 1, so you've got A7 equals 1 times 2 raised to the 7 minus 1 power. Now, multiplying something by 1 doesn't change it, so really what you have here is 2 to the 6th, and that proves that we were right. It's 64, and I did it down here again too. 64 is the 7th term in this geometric sequence. Now, Excel, like I said, can do this for us too. Excel is very smart. Watch this. So the first terms were 1, 2, 4, 8. They gave us 1, 2, 4, 8, 16. Okay. So as long as Excel sees the pattern, I can just drag this down as far as I need. Oh, wait a minute, something went wrong. Oh, you know why? Because yeah, I didn't do it correctly. It should be okay now. All right, so we're interested in term number 7, and there it is. Okay. So now you know what a geometric sequence is, and you've had some experience calculating the term that we're looking for. So we'll do several of these examples on Monday, and we'll also show you how to do a sum of geometric terms. And then this chapter will be done, and we can dive right into 6. Okay, and 6, like this chapter 5, will contain a lot of concepts that you've seen before, but maybe you haven't thought about them in a while. And so some of it will be like, you know, kind of like a reunion with old friends, and some of it might be completely new. All right, so I guess there's nothing else for us to do today. There's no last minute questions. I'll see you all on Monday. And also don't forget, if you're watching the videos from today, most likely there will be 2 of them because of the interruption that when I had to reboot. So, but I'll label them parts 1 and part 2, so you'll be okay. All right, so are we done? Does anyone have anything to say or ask? If not, I'll see you all on Monday. Now, by the way, I've been reading that the weather is supposed to be pretty awful tomorrow. So just be careful. Okay, it looks like we're going to get a lot of raining and flooding again, like we need more flooding. So just be careful, everyone. And I'll see you on Monday.
Thank you.
You're welcome.
Thank you.
Thank you.
Professor.
Take care.
Bye.
Bye.